Welcome. In this tutorial, we will learn about how to connect and configure non-contact displacement transducers with a data acquisition system. Let's get started. Step 1. Locate and review the manufacturer's datasheet for your specific non-contact displacement transducer. Before making any electrical connections, it's important to note key parameters, namely, the physical measurement range, the available output options, and the required supply voltage. For this specific tutorial, we'll be working with a 4 to 20 mA analog current output model, which needs 12 to 24 volts DC excitation. Step 2. Map out the sensor's wire color codes and their functions. The brown wire acts as the positive power input, connecting directly to the positive terminal of your external power supply. The blue wire serves as the 0-volt ground return, connecting to the negative power supply terminal. The white wire carries the 4 to 20 mA analog signal output, routing real-time measurement data straight to your DAQ input channel. Together, the brown and blue wires power the sensor, while the white wire feeds the measurement signal into your acquisition system. Any unused wires should be properly insulated to prevent short circuits. Step 3. Review the DAQ connector pinout configuration. Refer to your DAQ hardware manual to verify the correct pin locations for an analog current input. Examining the diagram, our primary objective is to locate the measurement signal lines. Pin 13 maps to signal plus, while pins 9 and 4 map to signal minus. As an alternative, if you choose to power the sensor directly from the DAQ module, you would use pin 12 for excitation plus and pin 11 for excitation minus. However, because our integration strategy uses a dedicated external power supply for this tutorial, these onboard DAQ excitation pins will remain unused. Step 4. Wiring the analog current configuration. Make the physical connections as shown in the diagram on the right. First, connect the sensor's brown wire directly to the positive lead of your external power supply. Next, connect the sensor's blue wire and the power supply's negative return wire together into pin 9 of the DAQ connector. Thereafter, insert the sensor's white signal output wire into pin 13, which serves as signal plus. Finally, install a shorting jumper between pin 9 and pin 4 to complete the circuit as per the pinout configuration. Step 5. Initialize the DAQ hardware and software. First, align and firmly plug your wired terminal connector into an available channel slot on your DAQ module. Next, power on the DAQ module and external power supply. Then launch your data acquisition software on your workstation. Ensure that the software automatically detects the hardware and establishes a stable communication link with the module. Also, verify that the NCDT sensor powers get on successfully after switching on the external supply, which you can confirm by checking that the laser emission light is active. Please note, for this demonstration, we are utilizing the QuantumX MX840B DAQ module and catmanEasy software. Once the software is launched and project loads, locate the channel in the channel list where your sensor has been connected. To configure the sensor, search the sensor database on the right for your predefined template, or right-click the existing current sensor template and select Edit Sensor to verify or modify its parameters. Now in the sensor database window, right-click and copy the existing current output sensor template and paste in my sensors folder. Rename the new entry, let's say NCDT_current analog output. Next, move on to Transducer Characteristic tab to define how electrical signals will map to the displacement change of NCDT laser under 2-point scaling configuration. Map 4 to 20 mA electrical signals to your corresponding physical displacement range of 0 to 300 mm. Once configured, navigate to the Transducer Settings tab to ensure the excitation is set to 0 volt. Click on Update Sensor to save this sensor profile. Back on the channel assignment screen, search for your newly created sensor profile in the database panel. Then double-click or drag it to assign it to channel 1. With the sensor profile assigned, the live measurement instantly updates to show active current readings. Click Zero Balance to tear the baseline. As you physically displace the laser target, observe the real-time displacement values updating in catmanEasy, confirming a successful configuration. Your sensor is now ready to record live displacement data during testing. If this quick guide helps you get set up, hit the like button and subscribe for more instrumentation and testing tutorials.